Welcome back, ladies and gentlemen. We are now on day 2 of chapter 5. We're still in section 5.1, and today we'll be discussing simulation. By the end of this lesson, you will be able to use simulation to model chance behavior. As usual, try this assignment after we are done with the lesson. Let's begin. All right, so 5.1, day 2, simulation. You can read much of this information on pages 332 to 335. And what is simulation? What is the purpose of simulation? Now, the definition, a simulation imitates a random process in such a way that simulated outcomes are consistent with real-world outcomes. Now, the purpose of this is to estimate probabilities when they are difficult to calculate theoretically. All right, so when we can't use normal curve calculations, when we can't really use the basic rules of probability, when we can't use any other system, then we use simulation. Right? It's kind of like our last resort. So how do we design and carry out a simulation? All right, step 1, describe how to use a random process to perform one trial of the simulation. Tell what you will record at the end of each trial. Step 2, perform many trials of the simulation. Now notice this word many. Remember last lesson, we discussed the fact that 50, 100, a couple hundred, that doesn't really qualify as many. Many would be like thousands of trials of the simulation, which is why this is our last resort. Now, we can use inference based on fewer trials, but keep in mind that the fewer trials we do, the more variable our results might be, and the less, the higher the likelihood that they will not actually be consistent with the real world outcomes if we were to do many more trials. All right, so beware of short run trials. Now for step 3, use the results of your simulation to answer the question of interest. All right, so some simulations that we've used this year. We did a lot of simulations at the start of the year with our hiring discrimination activity, when we were working through the caffeine experiment and distracted driving activity, when we did our sampling with sunflowers activity. We've done a lot of simulations. All right, so let's try a couple. So for example 1, suppose I want to choose a simple random sample of size 6 from a group of 60 seniors and 30 juniors. I want to be sure that my sample has 4 seniors and 2 juniors. To do this, I write each person's name on a slip of equal size paper and mix the slips in a large hat. I will select names one at a time from the bag until I get 4 seniors and 2 juniors. So in other words, after 4 seniors are selected, the remaining seniors will be discarded, and after 2 juniors are selected, the remaining juniors will be discarded. It takes 14 name selections to satisfy the requirement of getting 4 seniors and 2 juniors. Does this outcome provide convincing evidence that the names were not properly shuffled? And to help answer this question, we want to perform a simulation to estimate the probability that will take 14 or more selections to get the 4 seniors and 2 juniors. All right, so we're trying to determine whether or not we have evidence that the shuffling wasn't done correctly. All right, so for letter A, describe how to use table D to perform one trial of the simulation. Now remember, table D is our table of random digits. It's referred to as table D in the appendix at the back of our textbook. I gave you guys a printout at the start of the year that referred to table B. That was from a different edition of the textbook that used B instead of D in the appendix. We can just refer to it as the table of random digits so that we don't have to worry about what the letter for the table was. That part doesn't really matter. It's as long as you're using a table of random digits. So we need to describe how to use a random process. Table of random digits is a random process to perform one trial of the simulation. So we are going to label the 60 seniors, 0, 1 to 60. Remember, our labels have to be the same length. And the 30 juniors, 61 to 90. And that way our labels aren't doubling up. So numbers 0, 1 through 60 will identify seniors. 61 through 90, which is 30 more numbers, will identify the 30 juniors. And each individual number represents a different name on a different slip because these were actually named seniors. All right, so we're going to use pairs of digits from the table of random digits where repeats, we don't want repeats because these refer to individual seniors and the same person should not be selected twice. 0, 0, and 91 through 99 are skipped because these are not part of our labels. So we don't want to repeat our labels, and we don't want to use any numbers that are not part of our labels. So we're going to ignore 0, 0, 91 through 99, and repeats. So those are skipped. Now moving left to right across a row, we'll look at pairs of digits until we have 4 different labels from 01 to 60 and 2 different labels from 61 to 99. All right, that's just reinforcing that we are ignoring repeats. This part right here, moving left to right across a row, that's identifying how we're using this list of random digits, how we're going through that process. You need to be very specific when you're describing how to use a random process. Not everyone knows how. So in order to ensure that whoever is actually going to follow your method does it right, you actually have to be very specific. Include this statement, please. Right, now, once we've done that, we will count how many different labels from 01 to 90 we looked at. All right, so our trial is not over until we have 4 different labels from 01 to 60 and 2 different labels from 61 to 90. And once that's finished, then we count how many different labels we have from 01 to 90 that we looked at. So we're going to go through that with letter B. So perform 2 trials of the simulation using the random digits below. Make your procedure clear so that someone can follow what you did. All right, so I have my list of random digits down here, and I listed out the pairs of random digits that I was reading as I read this from left to right. And I have to finish one line before I start the next. All right, so my first line started with 1-5, so that would have been 15, and that would have represented a senior. I put SR for senior, and I put 1, so I could keep track of the fact that I had found 1 senior. The next pair of random digits right after the 1-5 were 1-8. When I write that down, I have 18, which also indicates a senior, and that's my second senior. Now, the 5 at the end of this grouping and the 3 over here, those are actually going to pair up. These are just separated into sections of 5 to make it easier to read so that your eyes don't repeat the same number twice as easily. All right, so 5 and 3 combined to give us 53. That's also a senior because it's within the labels from 01 to 60. And that's my third unique senior. Now my next pair is 95. 95 is not one of my labels, so I'm ignoring it. That's why I have an X here. My next pair was 19. That was a senior. That was my 4th senior. So any other seniors I'm going to ignore. All right, so my next pair was 12. That's also a senior, but it doesn't count as part of my sample. I still pulled that name out. I would still set it aside. All right, 83. 83 would count as a junior. That's between 61 to 90. So that would be my first junior. 41 was a senior, but I already have all of my seniors, so I would just set that aside. 51 is also a senior, but I have all of my seniors. I would set that aside. 14 is a senior, but I have all of my seniors. I would set that aside. 51, based on the description of the process we're trying to simulate, if you've already pulled someone's name out of the hat, you wouldn't have put it back again, so this wouldn't have been possible to pull, which is why we're ignoring it completely. These were names that could have been pulled, but we wouldn't have counted them as part of our sample. It wouldn't have helped us finish gathering our sample any quicker. This one can't even happen, just like numbers that we aren't using for labels. All right, so this one is excluded altogether. Our next one is 97. That one gets excluded also. It's not one of our labels. File number 87. That would be our second junior. We now have 4 seniors and 2 juniors, and took us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 selections. Remember, the numbers that are not labels would not have matched up with anyone's name, which means they wouldn't have been in the hat to be selected. Once we would have pulled someone's name, it would no longer have been in the hat to be selected, so this 51 could not have occurred another time, which is why these 3 numbers are not being counted when we count up the number of selections. That's why those just have a large X, and I'm only counting up numbers that would have corresponded to different seniors or juniors that were selected. All right, so then we will count up how many different labels from 01 to 90 we looked at. That's what I counted up for this 10. Now trial 2 starts right after the last one. This one left off at 87. 87 was right here, so my next number would be 61, which is a junior. 10, senior. 90, junior, so I have both of my juniors. 43, senior, so I have my second senior. 56, also a senior. 64. Now that one's a junior and I already have my 2 juniors. Now that name could have been selected and set aside, but it would not have been part of my sample. So I need to go back and get another number. 42 is my 4th senior. So I would have made 7 selections from the hat. Only these 6 would have counted as my sample, but I would have made 7 selections. Now, going back to the goal of the problem, right? We were asked, does this outcome provide convincing evidence that the names were not properly shuffled, because it took 14 name selections to satisfy this. So we were trying to estimate the probability that will take 14 or more selections in order to get the 4 seniors and 2 juniors. And that's why down here, I'm identifying what happened. There were 0 trials of the first 2, so there are 0 trials out of 2 in which the number of selections was 14 or greater. When you perform some of your trials, you then need to write down the outcome, which is actually estimating the probability that will take 14 or more selections. Now keep in mind, we can't really use this one for inference because we only did 2 trials. That's not many repetitions. But this demonstrates that you know how to use your method. All right, let's go to the back side. Now in 50 trials of the simulation, there was 1 instance for which the number of name selections was 14 or greater. Do these results give convincing evidence that the names were not properly shuffled? Now what you want to look at for that is that either the names were properly shuffled and this just happened due to chance, or the names were not properly shuffled and the 14 or more selections that we had to make was not due to chance. So when you look at 1 instance out of 50, 1 instance out of 50 is a 2% chance that it would take 14 or more selections. Now that's extremely unlikely. In fact, it's so unlikely that we would reject the idea that those names were properly shuffled. It's more likely that they were not. So yes, this gives us convincing evidence. There's about a 1 out of 50 or 2% chance that it will take 14 or more selections if the names are properly shuffled. Because this probability is small, 2% is less than the 5% cutoff that we use for convincing evidence. We have convincing evidence that the names were not properly shuffled. All right. So this ties back in with what you learned in chapter 4 with the definition of convincing evidence and statistically significant results. All right. Now I have one more simulation here that takes this in a slightly different direction that I do want to go over with you. Now this should actually be example 2, not example 3. All right, so suppose that a basketball announcer suggests that a certain player is streaky. That is, the announcer believes that the player makes, if the player makes a shot, then he is more likely to make his next shot. As evidence, he points to a recent game where the player took 30 shots and had a streak of 7 made shots in a row. Now, is this convincing evidence of streakiness, or could it have occurred simply by chance? Assuming this player makes 48% of his shots and the results of a shot don't depend on previous shots, how likely is it for the player to have a streak of 7 or more made shots in a row? All right, so to carry out a simulation, so we're just going to set up the simulation for this one. We're not actually going to carry it out. So to carry out a simulation estimating the probability that a 48% shooter who takes 30 shots in a game would have a streak of 7 or more shots made, begin by assigning digits to outcomes. Now, the 48% here is stating the likelihood of him making a shot. And if we're going to simulate the 30 shots that they made in a game, like the 30 shots they took in a game, then we need to simulate 30 outcomes in a row, one outcome being the player made it, the other outcome being the player did not make it. So our random digits are not going to represent a sample or names or anything like that, so we want to include repeats. What we want our random digits to represent are the likelihood of yes versus no. Did they make it or didn't they? All right, now because of that, we're going to assign 1 to 48, they made the shot. 49 to 100, they missed the shot. Now I'm going to do this with a random number generator. So 1 to 48, they made the shot. 49 to 100, they missed the shot. That gives us a 48% relative frequency of making his shots. Right? That's his current statistic for made shots. And then we're going to generate 30 random integers from 1 to 100 to simulate taking the 30 shots. And we're going to do that with a random number generator. So record whether or not there is a series of at least 7 makes in a row among the 30 shots. So we're going to generate 30 random integers from 1 to 100. We're going to include repeats because now the 1 to 100 just represents made it or didn't. We want that probability to stay the same throughout. And we're going to record, so we record all 30 shots, and then we identify whether or not there is a series of at least 7 makes in a row amongst the 30 shots. Right? That's one trial. Perform many trials of this simulation. So you're going to repeatedly generate sets of 30 random integers from 1 to 100, counting up identifying whether or not there's a series of at least 7 makes in a row among the 30 shots. And then after you do that many times, see what % of the time there's a streak of at least 7 makes among the 30 shots. All right, so this is what you do when your % deals with probability as opposed to dealing with random selection from a population. As you can see, the integers are used a little bit differently. Now, what are some common errors when using a table of random digits? The common errors are not using labels that are the same length. We need to have labels that are the same length. Not addressing unused labels. You have to actually state which labels you're going to ignore, and if you're going to ignore repeats, which addresses this next part. So not addressing replacement issues. Ignoring repeats means that you're doing this without replacement. Failing to ignore repeats means that you are allowing replacement. Now this is the same with random number generator. For this one, you have to identify whether or not you are allowing repeats. All right, so please try this assignment, and I will see you in class.